we also introduced the concept of white noise, right? And we mentioned that the definitive property of white noise is that it has a constant spectral density. And the spectral density is nothing but the either the Laplace transform, or in other words, or also known as the Fourier transform, or the Z transform of the covariance function. So last time we talked about discrete white noise. Today I'd like to talk about continuous white noise. So today I'd like to talk about, I'd like to continue talking about white noise. All right. And I'd like to talk about, in particular, continuous time process, continuous white noise. And this type of white noise is a little bit more challenging or more complex to analyze than discrete white noise. And the reason for that is, I will mention that in a minute. But let's define what is this. So recall that we define white noise as a weakly stationary process with the spectral density S of x of omega is constant, equal to just constant C, right? So, so our definition of the white noise is a process that has a constant spectral density. This is the main thing, right? So the variance in the case of the continuous process is given by sigma squared of x, which is also equal to the covariance at 0 of x, right? Which is equal to 1 over 2 pi integration from minus infinity to infinity Sx of omega with respect to omega, right? And so we know so let's substitute by S of x or Sx. Okay, so if we substitute by Sx being constant, then I would have 1 over 2 pi integration from minus infinity to infinity C with respect to omega, right? Which is, as you can see, what can you say now about the variance of the function? Sigma x squared is actually, for the continuous case, is infinite. This what makes white noise in the, as a continuous process difficult to analyze because it has an infinite variance, right? This is different than in the case of discrete white noise. Discrete white noise, it has a constant also variance, as we showed last time. But for continuous, it has an infinite variance. So when the process has an infinite variance, right, it means that it's not realized. You cannot represent it as a physical system. It has an infinite power. All right, so so this means that sigma squared of x is infinite, right? So let's write the covariance in general. So in general, so I'm going to call this 1, okay? In general, the covariance function is given by 1 over 2, the covariance of the white noise is given by 1 over 2 pi infinite, the covariance of the continuous process white noise is given by 1 over 2 pi minus infinity to infinity e to the power of j omega tau c with respect to omega. For these integrals, I need you to refer back to the previous lecture. For those who were not here last time, I'm going to post the notes as soon as possible. I didn't have a chance to post the notes. If I didn't do that, by next lecture, please send me an email. All right? Yeah, so if you need the notes, I highly encourage you to take notes with me if you need to revise the notes right after the lecture, okay? Otherwise, you would have to wait for me until I post them online. Okay, so going back, so we have this, right? So actually, this is the Fourier transform of a constant. So this is nothing but a Fourier transform of a constant, right? So this is equal to C delta of tau. Right, and I'm going to call this second equation. So we have these two, equation number 1 and equation number 2. Equation number 1 shows that the variance, which is the covariance at 0, right, is infinite. Equation number 2, it shows that the covariance function in general for a continuous white noise process is actually the delta function. And the delta function is the pulse function, where it has like an infinite amplitude. Okay? But here it is multiplied by C, in this case here. So this is the pulse function, the delta function, or Dirac delta sometimes. So from let's write this. From 1, okay, we note that a continuous time white noise is not a second order random process, okay, which means, i.e., it does not have finite power. And is not realizable. Okay, so this is from 1. From 1, we see that the power is infinite and the variance is infinite, and thus it's not realizable. I cannot represent it as a physical system. All right. Okay. Let's continue. From 2, and 2 is here, which is the covariance as being the delta function. We find that any two values for the process, x of t and x of s, are uncorrelated. If t is not equal to s. So let's see that. So here, we see that r of x, the covariance is equal to the delta function, right? So, which means if you want to plot this, this is actually, so this is tau, rx of tau. So for any, actually this is t, right? So it's here. So this is tau, it's the delta function. Okay? Rx of s, if this is t, is here. So this is s, right? So for different values for tau, we have different delta, right? Which means what? Which means that this one and that one are uncorrelated, definitely uncorrelated. They don't depend on each other, okay? So we find that x of t and x of s are uncorrelated if t of s, if t is not equal to s, which is the same as in the discrete case, right? In the discrete case, we notice that the function is, or the process is uncorrelated, okay? So here I'm gonna write, which is the same as in the discrete case. All right. So what do we know by now? We know that for both discrete and continuous white noise, we know that we call a process white noise when it has a constant density function. All right. For discrete case, the function has a constant power too and constant variance. For the continuous case, the white noise does not have a constant variance and it does not have a constant power. Both of them, they are uncorrelated processes. Okay? So the only difference between the white noise, the continuous white noise and discrete white noise is that the continuous white noise has an infinite power, an infinite variance. All right, which makes the continuous white noise difficult to analyze and difficult to realize, meaning difficult to represent it as coming from a physical system, represented as a physical system. All right, any question?
Hey, Professor, did you say that the white noise in the continuous case has infinite power?
Say that again, Brayden.
Did you say that the white noise in the continuous case has infinite power?
I'm sorry, your voice was disconnected. Say that again, please, one more time.
Okay, can you hear me?
Yeah, now it's fine. Yes.
Okay. Did you say that the white noise in the continuous case has infinite power?
Yes. This is what I said. Yes.
Okay, I was just making sure I heard right. Thank you.
Yeah, no problem. So both of them have a finite density function, S of x, right? But one has an infinite power and one has a finite power. The infinite power case is the continuous case. All right. Okay, so now we have just finished chapter 2, right? And so with chapter 2, we talked about stochastic processes, different properties of stochastic processes, and also the spectral density, meaning that we also mentioned that you can represent a random process as in the frequency domain, right? By applying the Laplace transform or the Fourier transform on the covariance function. Right? If you apply the Laplace transform in the covariance function, you will get the spectral density, right? Which means what? Which means you can analyze the stochastic process in the time domain, right? But also you can analyze the stochastic process in the frequency domain. So all the tools that we learn in the frequency domain are applicable in this case here, okay? Which is really nice. And we ended this chapter, as you saw right now, by discussion on the white noise. White noise is very important, as you will see even in today's lecture. I'll talk about it later if I have the chance, in that we are going to use it as an input to a linear system, all right? And if you use it as an input in a linear system, you will see today that the output will be a stochastic process. So you have a deterministic process system. You apply a white noise or any random signal, you get a random output. Okay? The reason for that is because of the linearity and the stationarity, which is the timing balance, as you will see later. Okay? So white noise is important. And hopefully you will appreciate its importance as we move along in the course. So now I'd like to shift gears and talk about linear time or linear discrete time stochastic processes or stochastic systems. Now we move from a stochastic process to a stochastic system. Let's recall what's our definition of a system. A system is different than a signal or a function. So a stochastic process, my definition, like a loosely speaking or a loose definition of a stochastic process, is just a function. It's like a nonlinear function, right? It has some variables, arguments, and it has an output, right? A system is different. System has an input and has an output, okay? And typically it's a dynamical, we talk about dynamical system that has a memory, right? So stochastic process not necessarily has a memory. So what I'm trying to say is that when you think about systems, think about your definition for the deterministic case, okay? When you think about systems. Yes.
When you say stochastic systems, it means like deterministic system with stochastic input, or the
Yes.
system itself could be stochastic?
Well, right, we are going to focus on this, is that you have a deterministic system, you apply stochastic input to it. The system will be stochastic in that case.
And then as long as the system is linear, the output has the same characteristic of
You will
the
see
input.
today. This is today's topic. Yeah, you will see, yeah. This is what we're going to focus on, all right? I'm not sure if we have, so let's take it one step at a time, okay? All right, so chapter 3, which is linear discrete time stochastic systems. So in this case here, we are going to focus on linear and stationary systems. And I'm going to define what do we mean by linear and what do we mean by stationary systems. We are going to consider linear and stationary systems, at least in this chapter. Okay, so as in the deterministic case, we have different ways of representing systems. Can you tell me at least one or two? How can we represent a system, mathematically speaking? Anybody? Think in the deterministic case. How can we represent the system?
It's transfer function.
Transfer function, number one.
State space.
State space, which is what also?
Transfer function or ABC.
No, it's not. It's A, B, C, D, which represent what? Differential equations, essentially. Differential equations, essentially. Okay? But we put them in a matrix form, all right? With some tricks, so that differential equation, meaning if you have a second order differential equation, you convert it to a series of first order differential equations, and then you end up with the systems. So these are the two main forms of representing a system. We are going to consider them both here. So, okay, we're going to start with the transfer function method or models. Transfer function models. Okay. for transfer function, what do you recall about transfer function?
Relates output to the input.
That's true, number one. What's also a distinctive feature about
Frequency
it?
domain.
What's that?
Frequency domain,
Why it's in frequency domain? That's true.
because
Good job.
it's good for computational.
Yeah, but why?
Because in time domain you have to do convolution, here you just need to do multiplication.
Yeah, this is a result of that, which is true, but why it's in frequency domain in the first place? Because of this. It's in the Laplace, or in the convolution, the j omega. The omega appears in the transfer function. You will see what I mean in a minute. So typically, how we get transfer functions. So we have differential equations, okay? How do we get transfer functions?
Output divided by input.
Yes, that's true, but you have a differential equation.
You mean you have A, B, C, D?
No. You have a differential equation, you have derivatives. How do you get the transfer function? So you have like x dot dot is equal plus a x dot plus c is equal to some constant. Or is equal to the input, where x is the output and input is something else, u. How do you get x over u where you have a differential equation?
Laplace transform.
Exactly, you apply Laplace transform, right? So you move from the time domain in the differential equation to the S domain. And what's S? S is j omega, which is the frequency domain. Okay, so okay, but there is an assumption. Well, this is like an implicit assumption in most of the cases. When you do that, do you know what that assumption is?
Initial thing is
Your time. Initial conditions are zero. Okay, so there's an assumption there that when you consider transfer functions, initial conditions are zero. So these are all information we know from deterministic systems theory. Okay, so linear filtering. So let's consider. So today we are going to dance around these concepts, okay? So consider, so you have a system here. That system is represented by, remember we're talking about discrete case, either h of k or h of z, and the z domain, right? H of k, where k is the time instances. You have y of k or y of z, right? Which is the output, and you apply u of k, which is the input, or u of z. Okay, so you have a system represented by now what is h? It's another thing from deterministic systems. There is another way of how we determine the transfer function in deterministic systems. What's that way? And typically, it could be both in discrete or continuous, but for discrete. You mentioned it, it's convolution and it's the impulse response. It's using the impulse response. And we call that H of K or capital H of Z. So here you have the K domain or discrete domain, and you have the Z domain, which is the Z transform domain, okay? So let U to be the unit discrete pulse. Okay, so U of k is equal to 1 when k is equal to 0, and 0 when k is not equal to 0. And so this is equal to delta k. So this is the pulse function. Okay, so let's now apply U, the input, to the system as the pulse function and see what happens. Okay, that's what we're going to do now. So what happens when you apply this input, right, to this system? What's y is going to be? So y, So y of k is going to be equal to what? It's actually going to be equal to h of k, and k is equal to 0, 1, and we call that the impulse response. And notice all this discussion so far, right? There is no talk about stochasticity here. We are only talking about deterministic system here. So this is in fact actually a revision, right, of what we know about discrete systems. So, okay, so let's apply now, applying the Z transform. So if we apply the Z transform, we will end up with H of Z is equal to, so this is the definition of the Z transform, right? K is equal to minus infinity to infinity H of K Z to the power of minus K. All right, so, and this is what? This is the transfer function of the system. So this is the transfer function of the system. All right, so you see here we applied a pulse to the system, and we ended up with the impulse response. Okay, so if we apply the Z transform on this pulse response here, we get H of Z. This tells you what? What can you say about this? Is a fundamental result, right? It's very, very important, and this makes the impulse response very valuable. Why? In other words, okay, we have a system. Okay, I told you that here's the system, and also I told you, let's imagine that I told you here's its impulse response. Here's a system, black box, you don't know anything about it. But also here's its impulse response. I applied pulse, and this is what I got. What can you say?
Transfer function of the system, if you apply another input, this can be used as a
Exactly.
representation of the.
Thank you very much. Which is very powerful, right? Because knowing only the impulse response, you know the system, and you know the response for any other input. Right? And this is one way of what we call it system identification. One way to identify what a representation for the system. So it's very important, okay? Knowing the transfer function is very important, and this is one way of knowing of how we know a transfer function. Okay, so we can now obtain, and here's another assumption that is going to happen here. So now we can obtain the output response, right, y of k, for a causal linear system that is h of k is equal to 0 if k is less than 0. For any input u of k, where k is equal to 0, 1, and so on. Okay, so but here there is also another implicit assumption, which is causal. So we are adding another assumption. Okay, so we're going also now to talk about causal systems. In causal systems, you know what causal means? You remember what causal means? Causal system. It means that the input does not, the output does not precede the input. Meaning, there are some cases, not physical cases, where the output comes before the input. It's not realizable, but we call that non-causal system. So a causal system is that the output happens at the same time as the input or after applying the input. If the output happens before the input, the system is not causal. Okay? These systems are not designed in real life. They cannot be even. You can realize, I guess, a non-causal system in software using algorithms, right? But I don't think you can realize it in hardware. You can build it in hardware because it's like predicting the output for input that's not happening. It's not possible, I think. Okay, maybe it's possible in real life, but I haven't seen it. Anyways, beside the point. Okay, anyway, so the point here is that we're assuming that the system is causal. Okay, the output happens at the same time as the input, right? Or after it, after we apply the input. So this is like, okay, let's go. So what we just said right now is the following. We just said that, okay, now by applying the pulse input to the system, we get the impulse response. And by applying the Z transform on the impulse response on H of K, we get the transfer function. And once we get the transfer function, now we can find Y of K for any input U of K. And that Y of K actually, so here as Y of K is equal to the sum of N is equal to minus infinity to K H K minus N U of N, which is also equal to the sum N is equal to 0 to infinity H of N U K minus N, right? And that is equal actually to the convolution, right? We call that the convolution between the impulse response and the input. Yeah. So this is called, because it's discrete, so convolution can be an integral convolution in the continuous case or convolution sum in the discrete case. Convolution sum. Right. So right now I'm giving you this out of the blue, but actually we can show how we got this. So I'm telling you now that Y of K for any input, okay, can be obtained by the convolution sum between the impulse response and that input. Let's prove that. Okay, let's show that, at least show a sketch of that proof. So make it more rigorous. So we can show this result from the properties of linearity and stationarity. Okay, so let's apply the linearity first. So what does linear means? What does it mean? How do you know whether the system is linear or not? Anybody? Come on, guys. I guess we'll do it. Yeah? And you don't have to be correct, that's fine. I'm guessing that by looking at the system, you know that it's linear, right? So x dot is equal to ax. That's linear, right? It's linear in the x, right? In general, how would you know that the system is linear? So let me go back to my this comment. I mentioned x dot is equal to x. compared to x dot is equal to x squared. Right? So you see that x squared is nonlinear, ax is linear. Okay? In general, how would you know?
So for if the input, when the input gets like scaled or you know, the increased by a certain amount, the output gets scaled or increased by the same amount?
Yes. Something like that, yes. So if we apply an input, right, we get an output. And if we apply another input, we get another output. Now, the system is linear when it satisfies the superposition, we call superposition sometimes property. Now then, alpha u1 of k plus beta u2 of k will result in alpha y1 of k plus beta y2 for any scalar alpha and beta, which is similar to what Braden said. If you scale the input, the output will be scaled in the same way. Okay? If we have that, then we have a linear system. All right? So the examples about the differential equations I just gave earlier, right? We know them by practice or by intuition or whatever, right? But in fact, you need to see the relationship between input and output to determine whether the system is linear or not. Okay, so this is linearity. Keep that in mind. Okay. Let's go now for stationarity. Stationarity. Right? So stationarity, we talked about this in chapter 1 and 2, or at least, sorry, in chapter 2. And when we talked about the stationary stochastic process. So what does it mean? What does it mean, stationary? Anybody? Stationary. Give me simple description of what a stationary means.
Just like a delay in the response, the output also delays by the.
Okay, yes, but what in a simple terms, what does it mean?
The system doesn't change by time.
Yes, it's time invariances, basically. Okay, we talk about time invariances. Okay, system properties do not change with time. Okay, so this is, we also call it time invariance. Okay, which means that the properties of the system do not change with time. So, as Pooja said, if u of k will give you y of k, then if you delay the input, uk minus n will give you what?
YK minus.
Yes, will give you yk minus n. So this is n. Oops. Okay? By the same, it will be delayed by the same amount. All right. So let's put these two together. Right? We talked about linearity, we talked about stationarity. Let's put them together. So, okay. Response to unit pulse, right? Delta of k will lead to what? We just said that will lead to the impulse response. HOK. Okay? So how about response to pulse of density of intensity U0? So if this delta is actually has an intensity, right? U0. So this is unit pulse, right? If I apply, so this means I have U0 H of K. So I have U0 delta, right? That would mean you have U0 H of K, right? So U0 delta of K. So now let's apply linearity and stationarity. So because of linearity and stationarity, right? Okay, and if U is equal to U of L for K is equal to L and U is equal to 0 any other time, right? Which is the definition of the pulse, right? That means what? That means U of L, H, K minus L as a value that's not 0. Otherwise, everything else will be 0. So, all right? So this here, so this is actually, so it's not equal to 0 at K is equal to L, based on this definition. Now, let's apply a sequence. Remember, we're talking about discrete case. Let's apply a sequence of these pulses. So the response at time K to a sequence of these pulses will lead to this. Y of K is equal to the sum. So we sum all these at different cases, right? So the sum from I is equal to 0 up to K, UL, H, K minus L. And this is L, not I, sorry. L. So we sum over all these pulses. And this is what we started with. So this is what we wanted to show actually. Right? We can also show, so this is one way, but this assumes that we start the input at times equal to 0. But it's possible that we start the input at time minus 10 seconds, right? Or minus infinity. So in that case, if the input sequence starts in the past, then we have the following. Y of K is equal to the sum from N is equal to minus infinity to K, H, K minus L, U. All right, both are equivalent. Okay. Okay, now up to this point, we have been talking about deterministic systems. So let's recap what we did so far. Okay? Let's recap what we did so far. So what we did so far, we talked about a system that has an input and has an output and has an impulse response, H of K, and that has a transfer function, right? And because of this transfer function, I can find the output for any input, U of K, right? And actually the output is the convolution sum between H of K and U of K, right? And we are assuming that the system is linear and time invariant. Because of that, we can show this. And this is what I did here. Okay, right after here, this is me proving this result, this sum. Okay, based on this. Now, let's do this now. Now assume Now, assume that U is a stationary process. Okay, let's assume now that the input is a stochastic process and it's stationary. And let's see what happens. Assume now that U is a stationary, and this is where the contribution of this course happens, right? Because as before, we study only deterministic system, and we assume always that the input is deterministic, right? And because of that, the output will be deterministic. Now, we are going to assume that U is a stationary process.
U is input to the system.
Yes.
And it is stationary.
Right now, we're saying it's a stationary stochastic process. So stationary process, so the implication here is a stochastic. Okay, process with a given mean value mu and covariance function R. Okay, so we are assuming now there are assumptions here. So always pay attention to the assumptions. We are assuming here that U is a stationary stochastic process. We are assuming that we know its mean. We assume that we know its covariance. Okay? And we're assuming that the system is linear. We're assuming that the system is stationary. We're assuming the system is causal. Okay? All these. Let's see what happens. Let's see what the output is in this case. Then, okay, let's start with the mean of the output. Let's study what the mean of the output is. My of k is equal to what? The expected value of k. And here's another assumption. This is actually maybe not the most rigorous way one would do it, but there's an assumption now that y is stochastic. Okay? So we're going to see what is y of k. Let's see. So let's take the expected value of y of k. Right? That expected value of y of k is equal to the expected value of, right, this one. So remember, this is the, let's make this in the box. Okay, the expected value of this one, of y of k, it's given here. Okay, so expected value of the sum when n is equal to 0 up to infinity, h of n u k minus n. All right, now we can make sure, we know now for sure that y is stochastic. Why y is stochastic? Because u is stochastic. So this makes the right-hand side stochastic. Then E has a role here, and that role is, so H is not stochastic, will go out of the expectation. It's a deterministic transfer function, impulse response. So we get the sum out of out. So that this is equal to n is equal to 0 up to infinity, h of n, expected value of u k minus n. Right? And what's the expected value of u k minus n? Anybody? Mu, exactly. But k minus at k minus n. Mu k minus n, because u is at k minus n. All right. So this is the expected value of r. Okay, now let's go to the covariance of the output. Let's investigate the covariance of the output. So for the covariance, let's assume mean values are 0 without loss of generality. Okay? So remember, these assumptions, this assumption is a very mild assumption, right? So we assume mean values are 0 to do that, and then we end up with this. Ry of tau is equal to the expected value of y k plus tau y of tau. Right? This is the application of definition of the covariance. Okay? So now let's apply the definition of y. So this is the expected value of h the sum from n is equal to 0 up to infinity, h of n u k plus tau minus n, right? Times the sum n is equal to 0 up to infinity, h of n u k minus n. So one has a tau and the other one does not. Okay. So I'm going to call these star. Okay. And notice here that the impulse response is not random. Not random. The only thing that's random is the u, in this case here. Okay? Six. 7. So let's do this. So the covariance is equal to the sum. So covariance is equal to the sum from n is equal to minus infinity to infinity h of n. Right, we take the, because h is not random, we take it outside of the expected value, times the sum of n is equal to minus infinity to infinity h of l times the expected value of u k plus tau minus n times u k minus l. Okay, notice something here. Notice that we started with, by applying the definition of the y starts from n is equal to 0 up to infinity. Right? Now I'm saying that the sum starts from minus infinity to infinity. Well, this is just for convenience because later on I'm going to apply the z transform. And notice this is not significant because notice that h of k is equal to 0 for k is less than 0. Because of causality, because we are assuming the system is causal, so and we are starting u at equal to 0 and going forward, so that's why. All right, so because of that, it's okay for me to extend the limits. So this is the reason for this. Okay, instead of as opposed to starting from 0. Okay, because the negative for n negative values. This is 0, so it's okay to do that. And there is a reason for me doing that is, as I mentioned, I want to apply the z transform later on. And z transform is from minus infinity to infinity. Okay, also, look at this. Okay, what is this? What is the expected value of uk plus tau minus n times the uk minus l? What's that?
Covariance function
Good job.
Rx of
Good job, Pooja. Yes, It's the definition actually of the covariance, which is the covariance of the covariance of U, right, from K plus tau minus N minus K minus N, right, which is equal to the covariance of U, right? So now K will go with K, and we will end up with tau plus N minus N. All right, so now this means that the covariance of Y is going to be equal to the sum from N minus infinity to infinity H of N times the sum of N is equal to minus infinity to infinity H of L RU tau plus L minus N. Okay, so see what's going on here. The covariance of the output is dependent on the impulse response and the covariance of the input. Okay, I'm going to give you another result that's even more illuminating than this one. Okay, by taking the Z transform. Taking the Z transform of this one. Okay, so now let's do that. So take the Z transform of Ry of tau, right? By definition of the Z transform, it is tau is equal to minus infinity to infinity Ry of tau Z to the power of minus tau. And now you notice that this is the definition of the Z transform, starting from minus infinity to infinity. So that's why I added the minus infinity there. All right, so now let's now substitute by Ry from here and here, right? So then let's see that we have two summations, right? Plus this summation, so we'll end up with three summations. So the first one is from tau is equal to minus infinity to infinity times the summation of N is equal to minus infinity to infinity H of N times the summation of L is equal to minus infinity to infinity H of L Ru tau plus L minus N Z to the power of minus tau. Right? Now let's rearrange things a little bit. So this is the same as, because this does not depend on tau, this does not depend on tau, so I can take this sum here. So here I have the sum from N is equal to minus infinity to infinity H of N times the sum N is equal to minus infinity to infinity H of N times the sum tau is equal to minus infinity to infinity Ru tau plus L minus N Z to the power of minus tau. Okay, now let M is equal to tau plus L minus N. Okay, so if we do that, then the Z transform of Ry of tau is equal to let's do it on a different page. Right? So this means the Z transform of Ry of tau is equal to the sum N is equal to minus infinity to infinity Hn, and the sum N is equal to minus infinity to infinity H of L times the sum M is equal to minus infinity to infinity, right? Because see here, because when tau is equal to infinity, that means M is equal to infinity. And when tau is minus infinity, m is equal to minus infinity. So I can say that m is from minus infinity to infinity. Ru of m z minus m plus n minus l. Right? Now, this is like a power, right? So I can decompose this into z to the power of m times z to the power of n times z to the power of l. Z to the power of minus m, z to the power of minus n times z to the power of l. And then distribute it back because this is in the terms of n, this is n. So this is equal to the sum m is equal to minus infinity to infinity h of n z to the power of negative n times the sum of L is equal to minus infinity to infinity h of L z to the power of n times the sum m is equal to minus infinity to infinity Ru of n z to the power of minus n. Right? I'm going to call this the spectrum of Y in the Z domain. All right? Spectrum of Y in the Z domain. And this is what? Actually, if you look at these, what are they? Can you say anything about these? What are these? What's that?
Deterministic.
No. It's not that you have a covariance here. But what are these? Actually, these are the Z transforms of different things. So this one is the Z transform of 8. So let's write this. So this is the Z transform of the covariance of Y with Z is equal to e to the power of j omega, and it is called the spectral density. So from here, Sy of Z is equal to what? Is equal to the Z transform of H. We know that this is equal to H of Z, right? This one is the same as H of Z, but you have a positive power. So this is H of Z to the negative, right? And what is this? This is the Z transform of the covariance of the input, which is a spectral of the input. So look at this, take a minute and look at this here. We're saying here, so we just derived this relationship. The spectral density of the output is equal to the transfer function in terms of Z times the transfer function in terms of Z to the power of -1. This does not mean that this is the inverse of that, right? It's just different argument. Times the spectral density of U. All right, so this is very important. All right, so let's interpret this relationship, this expression here. So physical interpretation. So let me first, let's go back. Let's go back to here, to this one here. Okay? This is the definition of the covariance of Y, right? Definition of, I'm calling this expression as star, okay? So from star, we notice that Ry of 0 is equal to, so from here, if you substitute by tau is equal to 0, right, by here, so you'll end up with Y of k times Y of, this is, I think this is wrong. Stick here. Okay. So from star, we notice that R, the covariance at 0, which is also the which is the variance, right, is equal to the expected value of Y squared of k, right, which is the mean square value of power in the Y process. So now let's apply the inverse Z transform. So let's apply the inverse Z transform in that. So applying the inverse Z transform, we have expected value Y squared of k is equal to Ry of 0 is equal to, so this is the application of the inverse of the Z transform, 2 pi j over the contour C Sy of Z inverse with respect to Z, okay, which is equal to 1 over 2 pi j over contour C as the integration over the contour C, h of Z inverse. Now we substitute by Sy times Su of Z times Z inverse with respect to Z, right? Where the contour C is a circle in the region of convergence of Sy of Z. Okay, so this is the inverse Z transform of the covariance, right, at 0. So now, suppose h of Z, which is the transfer function, suppose that the process, the system actually, right, represents a narrow bandpass filter all right, center at omega 0. So what I'm trying to do here is I'm trying to show you the meanings of the covariance and showing you the meaning of the density function. So for this, let's take an example when the system represents a filter, bandpass filter. Okay? So if that's the case, so for Z is equal to E j omega, right? In the Z domain, Z is equal to E j omega. So that means when you multiply, when you have these cascade functions here, or transfer function, H of Z times H of Z inverse, right? Because Z and Z inverse are the conjugate of each other, right? So the multiplication here is actually nothing but the amplitude square. The amplitude of H e to the power of j omega squared. Okay, and because we are assuming that we are dealing with narrow bandpass filter centered at omega 0, so this is nearly 0, right, except at omega 0, right, because H is a narrow pass filter. Right? So, because of that, we can assume now the spectral density of the input, e to the power of j omega, is nearly constant at SU e to the power of j omega 0. So at the frequency omega 0, the density we can assume it to be constant because everywhere else this H, this amplitude is 0, right? So this leads to, and I'm going to end with this, the expected value of y squared of k is equal to the spectral value of the input, e to the power of j omega 0. But I can now take it outside, so now I can take the C outside of the integration because now I'm assuming it's constant, times 1 over 2 pi j, the integration of H of Z inverse times Z inverse, dz, right? So now I'm here, right? And because I'm saying now this is constant and applying the Z transform, the inverse Z transform of that, so that will be equal to the SU e to the power of j omega 0 times constant k, where k is a positive constant. Dependent on the transfer function H. Okay, so let me write one last sentence. So I'm going to call this double star, right? So from double star, the expected, so we can see here that the expected value of y squared k, or sometimes we call it the power of the y of the output, right, is dependent on the spectral density of the input. At least we can see it in this special case of the bandpass filter. Okay, in general, if SU is constant for all Z, we call the process white. Is white. All right, so I'll stop here. stop here. And so this is just an introduction to stochastic discrete time linear systems. All right, we just saw today that when we apply stochastic input, the output will be stochastic. And then we also saw how we can find the mean and covariance of the output, right? Based on the mean and covariance of the input. Thank you. Please read the chapter 3, okay? And let's meet on next week. All right, thank you.